Como acpe. Two didn't say? Weird. I don't know. What language is that? It's Pig Latin. Cool. It's not a real language. Well, maybe it is. I don't know what makes a language real. Anywho, we've been talking about the complex numbers. Now, within our study of the complex numbers, we've seen a few different things. We have seen the powers of I, right? It is a loop that repeats how many steps in my loop? 4. So anything I to any power can be rewritten as something in there. Now, as we look at this, we started looking at the basic operations. We covered addition and subtraction. Combine the real parts, combine the imaginary parts. Piece of cake, I hope. We stepped it up a little bit and did multiplication, which is also not terrible, I don't think, and I hope not. But we should probably go to first hour. Okay, from multiplication, we noticed something super handy. Real quickly, without writing it down, I want to see if we can get this one. I want to know, without writing any of it down, I'll write it on the board. If I take 2 plus 3i times 2 minus 3i, what do we get? I'm going to count down from 5, and we're all going to shout out the answer. Without foiling, there's a shortcut. 5, 4, 3, 2, 1.
4 ice.
So, I heard one person at least say it. Remember, if we're doing these, when I foil, the middle pieces come out, right? So all I really have to worry about is 2 squared is 4, and 3 squared is 9. Add those together. 13. It's 13 right off the bat. Every single time when we have this number times its, what's that called? It's not itself. It's the same except it's a minus in between. The conjugate. Okay, so we're going to continue on with that. If you are looking at that going, what on earth are you talking about, Holloway? It's this. This is the last thing that you have in your notes. We did the complex conjugate part and said, hey, look, there's always a shortcut. Okay, Lily, if you haven't watched a video, you're probably looking at this going, what the heck? Okay, the square root of negative 1 exists. Yeah. Yep, we had that conversation before you left. It's called I. They're called imaginary. Terrible choice. Cool. All right. Looking at stuff. So multiplication, addition, subtraction. There's only one operation left. Division. So here we are. Let's continue on. We are using dashes, I believe, for our operations. And the last little piece that we need to think about is division. Now, this one is not like your traditional division because we can't think of these complex quantities, a plus bi. We don't think about them quite as normal numbers. I isn't a length in our real numbers. You can graph them for sure. You have to change stuff around a little bit. But when we divide, it's not the same as asking, does this go into this necessarily? Our goal when we divide the complex numbers is pretty simple. We are only going to use division as a process to simplify expressions. Simplify expressions. And have I used ST in here much yet? Okay, so that's fine. Such that is what I use ST for pretty regularly. Simplify expressions such that, and I'll write it out if you, I'll do this, such that, no, or there are rather, I will write like a real person. Simplify expressions such that there are no imaginary numbers, and I'm just going to say i's, in the denominator. Okay, that is our goal. We want to just simplify expressions so that there's no I in the denominator. That's it. Okay, now when we do this, it turns out there's a pretty convenient thing that we can do, and the language, like, it works in a lot of different situations. We're going to see it specifically with the I stuff right now, but you're going to see the same technique repeat over and over and over in a variety of different types of problems. So without any further ado, let's just get into it. Example, all I want to do is divide. That's it. And let's get rolling. On our first one, I want us to determine what do we get if we take the number 7, and we're just going to write it as a fraction for division, divided by 2 minus 6i. Okay. Again, this is not saying how many times does 2 minus 6i go into 7. That's regular division with real numbers themselves. This is a little bit different. And we need to get rid of the I value in the denominator. Now, when we're doing these, we're going to use an equal sign because we're going to do something. We're going to let it ride from line to line. We're not manipulating two sides of an equation. We can't add something to both sides. We can't divide, things like that. However, everybody in here is aware of a special number. And whether you realize what that special number is right now, anything by that doesn't change it? 1. How many ways can I write 1? So I can write it like the number 1, right? Just a single 1. Any others? 1 over 1 would work. Any others? What's 3 over 3? 4 over 4? 2 plus I over 2 plus I? Anything over itself is a choice of 1, right? So when we're looking at this, we're going to tie together what we talked about yesterday. In your notes, what was the preceding idea? We defined something right above this in your notes. Not rhetorical. Look down at your page and then scroll up from where you are and tell me what the last definition we had. Complex conjugates. And what was the benefit of using a conjugate? If we multiplied something by its conjugate, like we did several times yesterday, when we look at these, here's a conjugate example. I had a complex and a complex with imaginary parts, right? Did my answer have any imaginary parts? No. Well, here's another one. A complex number and its conjugate. When we multiply them, does our answer have any imaginary parts? So it seems that if I can find the conjugate, we can get rid of the imaginary parts. Would you guys agree with that? Now, all it takes is a clever choice of 1. I'm going to annotate more than I normally do with the reminder that you guys can write as much or as little as you want, with the exception of I want you to at least write something. Okay, to think about this, we are going to immediately, with our first line, we're just going to start solving it. I need to multiply by a clever choice of 1. And I'm just going to make this comment, a clever choice of 1. And you will hear that over and over and over throughout this year. Okay, there's a infinite many way that we can write this number. However, there's only one conjugate of this. Based on the fact that we know a plus bi, and I'll write this up here just so we can reference it, but you guys have it in your notes already. What's a plus bi's conjugate? A minus bi. All we do is keep everything the same except we change the sign. So this is my complex denominator. It's not terrible, but it might look that way. What's its conjugate? So just the denominator. 2 plus 6i. But if it's a clever choice of 1, I have to multiply by a choice of 1. What has to go in the numerator in order for this number in green to be a 1? So if I do 7, Angel, I like the idea because you're trying to make it match with the other one. But the only way we can write 1 is something over itself. Conjugate over itself. So if we need to write that, you can. This is the shorthand for conjugate. We're just multiplying by the conjugate over itself, or conjugate over conjugate. Okay, now looking at this, that shortcut is super convenient, and right here's the immediate first time that we're going to see where it's convenient. If I do the numerator first, let's just distribute. What's 7 times 2? 14, and 7 times 6i. Everybody agree it's 14 plus 42i. Okay, the denominator, big moment of truth. Do we have to FOIL it? No, because there's a shortcut. If we want to do this really quickly, can you tell me the two coefficients? 2 and 6, right? They're the numbers the real numbers that are there. What's 2 squared? Plus, what's 6 squared? So 6 times 2, definitely. I like 36. Now, I'm going to do 2 more steps, and you may not think that you need them, and that's okay if you don't. Can I clean up that bottom real quick? It's 14 plus 42i over what? 40. Now, just by convention, when we write our answers, we want an expression that has that same form of a complex number, a plus bi. Now, people get goofed up on this part of fraction stuff like all the time, but we're going to talk about it in hopes of avoiding it. If I have an addition right here, can I split this and make them both over 40? So more generally, if I take 1 plus 3, and you don't need to write this one, over 4, is that the same as doing 1/4 plus 3/4? I'm allowed to do it if it's in the numerator. If I have this, 4 over 3 plus 7, am I allowed to do this, 4/3 plus 4/7? I don't think so. And I saw immediate change, but this is 4/10, right? That's 0.4 if we clean it up. I already know that this is like 1.3 plus something. There's no way that that's going to be 4/10. This, you cannot split it up if it's in the denominator. Numerator's fine. So that one fails, whatever. Help me split this up then. 14 over 40. there's my real part, my a value, if you will, plus 42 over 40. And whether you put the I right here or in the numerator, your call. Where do you guys prefer it? Numerator? Okay. Is there anything that annoys any of you about this last expression? We should probably simplify it, right? What goes into 14 and 40? So if I'm going to simplify this and show all the work, 2 times 7 and 2 times 20, right? What goes into these two numbers? 2, okay? So that's 2 times 21 over 2 times 20, and the I is still there. Now, only reason I'm doing this is if somebody out there likely does not enjoy fractions or simplifying fractions, and I'm just breaking it down. If I have a 2 over 2, what happens with them? They cross out because that's really just a what? What's 2 divided by 2 when I see them there? It's a 1. Now, somebody said cancel quietly under their breath, and I get it. I'll accept it. I prefer divides out. Okay. Looking at that, can we tell what the simplified answer winds up being? 7/20 plus 21/20 I. Whether it's in the numerator or denominator, or sorry, numerator or outside, I'm okay with either. All we have to be able to do to divide these things every single time, just find the conjugate. Every time. Okay. Looking at this, questions here before I ask you guys to do one or two at your desks. Feels okay? All right, let's see if we can get some wonky ones. I'm going to have you guys do 2 for me, and I'll come around and check. I'm going to get rid of this just for now so I can have both problems up here. On Bravo, I want you guys to do 3 plus I over 1 minus I. And on C, I'll have that up there for when you're ready. Awesome. Do it to it. Talk it out. I'll be walking around to answer and address questions as needed. And we'll meet up here in just a moment. Try these out. Easy things to do and easy mistakes to make. We got to be real careful with them. First of all, I have a complex or an imaginary number in my denominator. So I'm going to multiply by the what? I'm going to choose a clever choice of 1. How do I decide what I multiply by? It's the what of this? Conjugate. We're going to try that one more time. I don't need like high energy or whatever. It's Tuesday morning. I get that. But I need to make sure everybody has it. What do we multiply by? A clever choice of 1. We choose the conjugate. What is the conjugate of 1 minus I? 1 plus I. And because we can only multiply by 1, it better be 1 plus I over itself. Okay. Here, I was seeing people make a lot of shortcuts because you want the shortcuts to exist. They do, but only in certain places. The denominator is our shortcut where we have a complex number times its conjugate. That's our shortcut. For that, 1 squared plus, what's the number in front of I? 1. So what's 1 squared plus 1 squared?
1.
Try again.
1 squared plus 1 squared. 1 squared. Oh, 1 4. 1 to the power 4.
What's 1 squared, Sonny?
1 squared. 1.
1 plus 1.
Oh, 2.
There it is. Okay. Now, the 2 in the denominator, it's there. It will happen every single time because I'm using the a minus bi and a plus bi. I'm using this shortcut where this is just a squared plus b squared. Every single time that you multiply by the conjugate, that will work. Every time. Okay, now the numerator, is this the conjugate of this? So we can't use that shortcut anymore. What is the conjugate of the numerator, just to check? 3 minus I. So unless I have a 3 minus I written here, which I don't, and I'm not going to, we don't have anything else to do there. Except this lovely work. 3 times 1. Okay, and then I'm going to put this in my brain for a second. We agree it's 3i. What's the next one?
1i.
So I had 3i and one more I. I'm just going to jump forward. That's plus 4i when I do both of them. And the very last one, plus I squared. Now, one of these things does not belong, and we need to change them. The I squared. Well, gosh, what's I squared? Negative 1. That's by definition. If I is the square root of negative 1, then I squared must be negative 1. So I'm going to change this to a minus 1, and everything's all over 2. Is there anything that we could fix here? 3 and minus 1? I think it's 2 plus 4i. And then we have a choice here. I could do everything over 2, or since I'm going to split it, did I lose you? Where? So you said where did the, and then you never finished that. Which part? Sorry? I just haven't written it yet because we need to decide, do we want a single 2 or are we cool with splitting it up at this point? Because we're going to have to split it up anyway. I may as well just do it now. Somebody's looking at that and maybe not liking it. You can do a single 2 here. That's okay. I think it's easier to simplify here. What's 2 over 2? Plus, what's 4 over 2? And there's one more thing left. I. We get 1 plus 2i. Okay. This one. Easier or harder? Try this one. We'll meet back up. That one's tricky-ish. There's several different ways you can do it, and my guess is that you're probably going to be right, but I want to see which ways we come up with. I want you guys to try C together. We'll do the same thing if we need. Now, I would never want you to do this on every problem, but is this a complex number in the form a plus bi? So you say no, and I agree with you kind of. Could it be? What's the a value that's out here that we just chose not to write down? It's not a 1. Do you agree that that is still the same thing? 0 plus I. And now it looks a little bit more like it. When we're looking at this, if this is the number, the conjugate would be 0 what I? Minus. Now, I'm going to write it in the numerator with the understanding that I probably won't in the denominator. Do I really need the 0? So 0 minus I is just negative I, right? Like, we don't really need the 0 except to see the conjugate, which means if I multiply by negative I over negative I, is that a choice of 1 still? Okay, hook it up with the numerator. What does that give me? Negative 5i. And in the denominator, I'm going to take 2 steps. What's I times negative I? Negative I squared. Everybody's still on board here. Where did I lose you? Which part?
Wasn't that a 0 times 0 minus?
We could do that if you want, and I can FOIL it here if you'd really like. 0 minus 0 plus 0 minus I squared.
Wait, how about the 5 times 0?
It's still what?
Is it 0? 5 times
Yeah, so I could, and if you want me to write that, I can. It'd be 0 minus 5i with the understanding that that doesn't really matter. Okay, thank you for asking. Gosh dang it, what's I squared? I just don't recall it, sorry. Oh, so it's a negative I squared is negative 1? And what does my denominator turn into? I lost my I along the way. 1. So if I have negative 5i over 1, do I really need to write the over 1 part?
No.
Nope, I would just go one more step or skip this step entirely. I think it's just negative 5i. Cool. The conjugate is your friend. You should use it every single time. If you don't use a conjugate, you will know that you've made a mistake when you're trying to clean this up because you will not be able to get out of the imaginary stuff in the denominator. You have to get rid of it. Okay. Now, as we look at these, I'm going to show you something that I don't particularly love that your book presents it, but we're going to see it briefly with the understanding that I will specify very clearly on a quiz, on a test, when I want you to do this. Okay. So, what we wind up seeing here, and not all of it is rough, and I don't know that any of it's really rough, but the last little tiny section is naturally, as we're looking at these things, what we are dealing with in the end are the solutions to quadratics. So whether we call them the roots, the x-intercepts, whatever the case might be, we're really just looking at the solutions, the roots. Okay, in here, this one, I'm going to put a big star next to, because this is the strange one. Okay, I'm just going to say caution. Okay, for this, when we factor, and I know it's been a while, but run me through the list. The very first thing we always check. GCF. If it's a binomial, we check to see if it's a what? Difference of squares. If it's a trinomial, we check for what? Perfect square. If it's not a perfect square, or if you don't like perfect squares, that's okay. You check the leading coefficient, because if it's a what, is it nice? If it's a 1, so there's our leading coefficient of 1, our shortcut. And then if it's not 1, or you can't find it, or don't see it, you have to resort to grouping. Okay, that's where we've seen so far. Now, 99% of the time when we're solving quadratics, we are in the real numbers. Because you guys have never graphed nor seen graphs with the complex stuff, the I. If I have only imaginary solutions, we don't get to see it cross the x-axis because the x-axis that it's crossing is in the imaginary plane, and that doesn't show up on our regular graphs. I'm not saying it doesn't exist, but it's way beyond what we need to deal with in here. Okay, there are solutions, there's roots, we just don't get to see them on our real coordinate system. So as we're looking at this, one of the things that results from here is what is called the sum of squares. Now, I would not add this to the factoring checklist, but it's nice to see that it does exist. If we encounter, and we're very specific that we are working in the complex numbers, and it's stated somewhere, we can factor something like this, a squared plus b squared. If we have this, it is the sum of two squares. And we'll do some real examples here in a minute, but it turns out there's a way to make this work, and we've already seen it. If I do the conjugate times itself, I'm going to scroll up here for just a second. I'll give you guys a moment, because I'm going to look back at something. Actually, I can keep it here, and I want you guys to look at something. Up top, did we have anything that spit out a squared plus b squared in our notes? It's the conjugate times, or a number times its conjugate, right? That's how we take that shorthand, which means we now have a way to factor this. If we want, and very seldomly will we, but we can factor this thing as a plus bi. And if we look back at that same thing, we have the conjugate is all we need to get this rule. Here's our factorization. Okay. Now, with this, it is so unique. I would not add this to your factoring list, but just to kind of look at it here, let's say hypothetically we wanted to solve the following. So let's give ourselves a lovely sum of squares. Let's say it's x squared plus 81 equals 0. Now, there's two ways that this problem could be approached. Obviously, right now we're going to see it with the sum of two squares. If I look at this, and I'm going to add one more word to the directions to show you what it looks like when I specify, solve in the complex numbers. When you see in the complex numbers or anything like that, all that this really and truly means, right here, that statement, I is okay in our answers. And that's completely fine. We can have an I if we're told we're working in the complexes. So here we go. Let's apply this rule. Do we know the square root of both of these things? X and 9. Now, normally we check to see if it's a difference, so we can factor it as x minus 9x plus 9. That's fine and dandy. This is not a difference. It's a sum. However, we do have a way to do this. So check it out. We're just going to plug and chug through this formula. What's the square root of x again? Plus, what's the square root of 81? But since it's a sum of squares, what else has to attach to this? I. A plus bi. And as soon as I get that, my other one is x, what? Minus 9i. And that is still all equal to what? 0. Now, the zero product property, ZPP, just tells me I have two factors at this point. If I multiply them, I'm getting 0, which means one or both of them better be what? That was really fast. If two numbers multiply to be 0, at least one of them must be 0. That is ZPP, the zero product property. If I do a little scratch work, and maybe we don't need it, but I'll show it just in case. If I set my first factor right here equal to 0, what do we get for x? Say it again. Negative 9i, because I'll subtract that from both sides. I agree with you. Negative 9i. If we set this one equal to 0, I get x minus 9i equals 0. And what do we get for x? Positive 9i, and we're there. I got both of them. If I graphed this up on the board, would we ever see the x-intercepts? No. This parabola right here, you don't need to sketch it, but it's going to look something like this. Now, it does cross and it has solutions, but when we graph the regular number system, we only put real numbers here and real numbers here. We just can't see it. If we want it, and we won't in this class, but maybe some of you will someday, is there a third dimension that we just don't include? And normally we would call it z, so it's like our normal three-dimension space. But if I made it I, which we could, the imaginary numbers, we would see a different picture here. And what we ultimately wind up with is, it's actually called a saddle, but it would actually look like a Pringle, like that shape of that chip. In a three-dimensional space, it looks like a Pringle, and there's places where it crosses the axis. We just don't get to see them here. Okay. Alternatively, and we have like 3 more minutes maximum on this. Here is one way that we can get it, sum of squares. I'm going to be completely honest. I don't like it. I don't like the sum of squares. It's not that it's hard or gross, but I think it gets factoring kind of ugly. Your book stresses it, so I'm going to make sure that we see it. In contrast with that, rather than finding it through the sum of squares, the other way that's much more natural in my head is by using what is called the square root property. Now, we have a whole system set up for solving equations, and this is really the square root property of equality, if you'd rather, but that's kind of gross and ugly. If I have an equation, and I know it's equal, if I add 5 to one side, what must I do to the other side of the equal sign? Add 5. If I multiply something by 3, the other side must be, they have to match, right? Now, if we look at this same problem, and we're going to see the same answer show up, but we're going to solve it a different way. We can take the square root of both sides of a number, or equation, sorry. The only thing that I'm worried about is always add plus or minus if introducing the square root or a radical symbol. And I'm just going to write it that. Always add the plus or minus in front of it if you introduce this into a problem and it's not just a variable. If introducing square root, I'm going to say to a number. Okay. Every single time this must happen because everybody always has a positive square root and the negative is easy to overlook. We'll just make sure that we stress the importance of it. So here we go. We're going to do the exact same thing. Example, solve in the complex numbers. And we're going to look at the same thing, but we're not going to factor it this time. We're going to do it slightly different. So here we go. X squared plus 81 equals 0. I'm just checking to see where people are with writing. Did anybody feel like it was really natural to factor that just now on the first part? Okay, awesome. If it feels natural, that's good. That's better intuition than I have. It feels really unnatural for me. I've literally never seen the language called the sum of squares. Like I knew it existed, never seen it in any textbook ever. Okay, on this one, if we didn't want to factor it and we're trying to solve this, anybody have a gut feeling or like a first instinct of what you might do? So I heard leading coefficient, which maybe we can think about it. You're not going to find factors of 81 that add up to a 0x if we think about the trinomial grouping stuff. Could I subtract 81 from both sides? Now, Mark's suggestion was to take the square root of them, which I don't mind that idea, but don't write this down. I just want to check something. Do you guys know the square root of 4 and 9? Okay, do you know the square root of 13? So if we don't know that, check this out. Do you agree that 13 is 9 plus 4? Can I just take the square root of 9 plus the square root of 4 here? You say that, but what's the square root of 9? And the square root of 4? So if we did this and we said, oh, this 3 plus 2, is the square root of 13 5? Can we split a square root like that then? Not allowed. You have to be able to multiply them. You can't split up addition and subtraction in a square root. Okay, with that in mind, let's subtract 81 from each side. I then end with x squared, or I'm at the point rather, is negative 81. Now, this is a much more natural approach to this problem for me. If I want to solve for x, unfortunately right now it's squared. But how do you undo a square? And if I take the square to the left side of this equation, then I'll also do what? I'll do it to the right side. So I'm going to add an extra line just so we can see it happening. Here's the square root here. And I'm going to add the square root here with an awkward gap in front. I left this gap for a very particular reason. What do we have to add? Mark loudly exclaims plus or minus. We introduce the square root of a number, it's required. Okay, I'll do the left side. The square root of x squared is x. And I want you guys to help me with the right side. How can we think about root negative 81? How do you even get to 81 and a negative 81 for that matter? So you're right. I'm going to go 2 steps out. Do you guys agree it's negative 1 is needed and then it's just an 81? Now, I'm viewing this because my thought is that you guys are going to recall this. Bless you. I'm going to move that up just a little bit so I can write it on the very last line. What is the square root of that negative 1? So there's an I in it. And what's the square root of 81 itself? We just found it's plus or minus 9i, doing the square root property. What did we say it was when we did it with factoring? Is this the same thing as plus or minus 9i? We're done. Okay, tonight you are going to see a little bit more of this type of stuff with the square root property and those good things. And we have just enough time. How much time do I want you to spend on homework each day? Maximum 40 minutes, right? So this evening, before you peace out, it's the 14th. And let's see, that was lesson 2.4 conclusion. We'll just say complex. This evening, you get homework 2.4.2, which you will find waiting for you on page 88. I want you to do 29, rather. We went through 27 yesterday, right? 29 through 45 odd, and 46. All right, quick check, just so you're not killing yourself. Juniors, tomorrow, what are you doing? You're doing the PSAT. So I'm actually going to change this. 10:14. Okay, I will collect this on Thursday. Juniors, you will not be in this class tomorrow. You're doing the PSAT, I believe. Sophomores, we'll figure out what we need, whether it's like just review of this stuff or if you want to do something sneaking ahead. We'll do something chill. I'm not going to have half the class miss a lesson. Cool. All right. I said it's due the 14th, but today's the 14th. What was I supposed to say, do you think? 16th. I don't know what I was doing. All right. Appreciate you guys. And 46. I'll write it back on the backboard as well. All right, you guys have a wonderful day, or don't. I'm not your boss. Although I think my picture idea is awesome and hilarious, I want you guys to smile nicely so your parents don't blame me for you frowning in your pictures. Cool.